Hello, and welcome to our lesson on precision DACs. In this video, we will talk about the endpoints of the DAC transfer function and how they deviate from expected. Achieving a true full-scale output, meaning that the output is exactly equal to the reference voltage, is not possible. Every DAC has 2 to the n possible number of codes, and the 3-bit DAC transfer function illustrated here reflects this. There are 2 to the third power, or 8, codes ranging from code 0 to code 7. Code 0 always maps to an output of 0 volts, so this means that the last available code, 7, maps to 1 LSB less than the input reference voltage. This non-ideality, known as 2 to the n minus 1 error, is unavoidable and is part of the ideal DAC model. But fear not, this error is generally not very large, only the size of 1 LSB. For a 16-bit unipolar DAC and a 5-volt reference, the maximum code will be a mere 76 microvolts, 1 LSB, away from the true reference voltage. Now to true non-idealities. Full-scale and zero-scale errors are not part of the ideal DAC model. In fact, these errors don't relate to the DAC architecture itself. Rather, they relate to the output amplifier that the DAC core uses. These are the same errors that you expect to see on any discrete amplifier. Therefore, the same solutions applied to amplifiers can be implemented here. Adding headroom or footroom can reduce the effect of zero-scale and full-scale errors. Full-scale headroom is very straightforward with most devices. Just increase the supply voltage above the reference voltage. For zero-scale error, lowering the ground pin below ground is not always feasible since the zero-scale error will vary from device to device, but there is a small solution that can be implemented. This is a simple circuit that makes the output of the amplifier never have to get too close to ground. Note that this solution requires that the feedback pin of the DAC is exposed, and it also requires a negative supply rail. To explain this circuit, let's assume that it works, placing 0 volts at Vout. In order to get this 0 volts, the resistor network output will also have to be 0 volts. Remember that the zero code error is not caused by the DAC but by the output buffer, meaning that 0 volts from the resistor network is possible. This will cause no current to go through the RFB pin and will make the VDAC node to be at a higher potential than ground, which will make the amplifier behave more linearly. If we look at an example with numbers, then we can see that the 1 milliamp will travel through the 100 ohm resistor and make the VDAC node be at 100 millivolts, which is high enough footroom for the amplifier. Thank you for watching this video on endpoints of the precision DAC transfer function and how to mitigate zero code and full-scale error. Please watch our other videos on precision DACs or go to ti.com/precisiondac to learn more.